Okay, so let us continue the third part of today's class. Okay, so in the last part, we have taught to this equation, and we call this equation equation 4. Okay, finally substituting equation 4 into equation 2, we get C real is equal to this equation. In equation 2, we can see that this term can be replaced by this term. So we directly copy this term and paste here to replace this term. We call this equation 5. So C real is equal to 1 over 2 times log 2 of determinant of I plus 1 over sigma squared times H times RSS times H transpose. So this finishes the solution. Insert QED and align right. Do you have any questions? Good. If you do not have any questions, let us go to, I think I need to save this. Page 105, problem 1. Blackboard Mimo. Let us go back to the slides. So we have derived this equation 2.33. The expression for MIMO capacity in equation 2.33 has units of bits per channel use. We can see that the unit of equation 2.33 is bits per channel use. What do we mean by this? First, the fundamental unit of capacity is the bit, because the base 2 of the logarithm is used. Second, the amount of information that is conveyed is the amount that the receiver learns by examining the received signal R at a given instant of time. That is, as a result of one use of the channel. So this is the meaning of channel use. We will show shortly that the unit of bits per channel use is equivalent to bits per second per hertz, which is what is normally referred to as spectral efficiency. Do you remember what is the spectral efficiency? The spectral efficiency of a communication system is the number of bits you can transmit within 1 second and within 1 hertz of bandwidth. An alternative form for the capacity is to specify it in terms of bits per second. To do this, consider a band-limited signal with bandwidth W and duration T. Do you remember what is a band-limited signal? That is a signal of its bandwidth is limit limited. That is, the bandwidth of the signal is not infinity. The Nyquist sampling theorem states that such a signal can be completely represented with two TW independent samples. Okay, because for each sample we must sample 2 times the bandwidth. Okay, 2W. Okay, for each second. Sorry, not for each symbol. For each second, 2W. And the duration of the signal is t second. So there are totally 2 TW independent examples. Okay, let us see reference 59. Okay, reference 59 is a book written by John Proakis and Mesut Salehi. And the title of the book is Digital Communications, 5th edition. Okay, published in 2007. Okay, if I remember correctly, this is the textbook of the course Digital Communications. Okay, let us go back to page 109. Okay, this means that it is possible to transmit this signal using 2 TW samples transmitted over a period of time equal to t seconds, which is equivalent to 2W transmissions per second. That is, within a second, the number of transmissions is equal to the 2 times the bandwidth. Okay, 2W. Since each transmission is capable of conveying the amount of information specified by equation 2.33. Okay, let us see equation 2.33. Okay, this equation. It follows that the capacity in bits per second is obtained by multiplying that expression by 2W. Okay, that is, okay, bits per channel use, and the number of channel use is 2W. Okay, per seconds. Okay, so after multiplying this equation by 2W, we have serial is equal to W times log 2 of this term, bits per second. Okay, which results in the following alternative expression for the MIMO capacity of a real signal. Okay, we can see that serial is equal to W times log 2 of the determinant of I plus 1 over sigma square times H RSS H transpose bits per second. We conclude from this discussion that since W times C, where C, the unit of C is bits per channel use, is equal to C, and the unit of C is equal to bits per second. Okay, you may have a question here. Why can we omit the factor 2? Okay, didn't we multiply the expression in equation 2.33 by 2W? Why the factor 2 disappear? Okay, because we are discussing about the unit, so we can omit a factor 2 or a constant 2. It will not affect the unit. Okay, So the units of bits per channel use is equivalent to bits per second per W. Okay, this bits per second, and we divide, we move the W to the right hand side of the equation. So on the right hand side is the unit is bits per second per unit of W. Okay, that is the bandwidth, or equivalently to bits per second per hertz, as was claimed earlier. Okay, so bits per channel use is equivalent to bits per second per hertz. Okay, as we claimed, okay, in page 108, bits per channel use is equivalent to bits per second per hertz. Okay, next, let us consider the complex signals in section 2.8.2. Okay, the expression for the MIMO capacity with complex signals is similar to the capacity for real signals derived above, except for two differences. The first difference can be deduced. Okay, what is the meaning of deduced? Let us see the handout. Okay, handout chapter 2 today. Okay, and find the word deduce. Okay, and on page 114. Okay, problem 1. What is deduce? Solution: to reach an answer or a decision by thinking carefully about the non-facts. Okay, let us go back to the slides. From the fact that complex signals consist of real and imaginary components that are capable of transmitting independent strings of information, hence we would expect the capacity for complex signals to be twice that for real signals, all else being equal. Okay, this is also the reason why we need to use the complex number to express a signal. Okay, because we can have the double capacity. The second difference, while somewhat less obvious, can be viewed as a generalization of the transpose operation on H in equations 2.33 and 2.34. Okay, let us go to equation 2.33. Okay, you can see that, okay, here is an H transpose. Okay, here. And equation 2.34, okay, you can see that it is also an H transpose here. Okay, let us go back to page 115. In Teleter's paper, he shows that with complex signals, the term H transpose should be replaced with H Hermitian. Okay, do you remember what is H Hermitian? That is the conjugate transpose of the matrix H. Thus, the expressions for capacity of a MIMO system with complex signals are given by the following. Okay, first, C complex if the unit is bits per channel use. The capacity for a complex signal is log 2. Okay, you can find that the factor 1 over 2 disappears. Log 2 of the determinant of I plus 1 over sigma square times H RSS H Hermitian. Okay, you can know that the transpose is replaced by the Hermitian. And if the unit of the capacity is in bits per second, then the capacity of a complex signal is equal to 2W, okay, times log 2 of the determinant of I plus 1 over sigma square times H times RSS times H Hermitian bits per second. Okay, you can know that for the serial there is no factor 2, and for C complex there is a factor 2 here. The approach in this section has been to use simple plausibility. Okay, what is plausibility? Okay, let us see the handout. Page 117, problem 1. What is plausibility? Okay, solution. Seeming likely to be true or able to be believed. Okay, let us go back to the slides. Okay. Plausibility arguments to justify the expressions for the capacity of complex signals rather than to show rigorous proofs. Okay, what is rigorous? Okay, let us go to the handout. Problem 2, what is rigorous? Okay, solution. Careful to look at or consider every part of something to make certain it is correct or safe. Okay, rigorous. Okay, if you translate the word rigorous to Chinese, it should be 严谨的. Okay, next page. This was done because the complexity of the mathematics is significantly greater when complex signals are introduced without a concomitant. Okay, what is this word? Concomitant. Let us see the handout. Okay, page 118, problem 1. What is concomitant? Solution. Something that happens with something else and is connected with it. Okay. Let us go back to the slides. Okay. Without a concomitant increase in added insight. For a rigorous derivation when complex signals are present, the reader is referred to Taylor's original paper. Okay, I think I need to explain the meaning of this sentence. Without a concomitant increase in added insight. Okay, what does this mean? That means you only can see some mathematics derivation, okay, but you cannot know the deeper meaning in the field of telecommunications. Okay, next let us see reference 70. Okay, reference 70 is a paper written by Henry Taylor. The title is Capacity of multi-antenna Gaussian channels. Okay, which is published in European Transactions on Telecommunications in 1999. Okay, let us go back to page 118. Okay. Although capacity formulas are presented for both real and complex signals in this chapter, in practice, most signals in actual MIMO systems are complex. Okay. Why? Okay, because we have explained we use the complex number to represent a signal can double the capacity. For this reason, only equations 2.35 and 2.36. Okay, let us go to equation 2.35. Okay, it is the C complex. Okay, is this equation in bits per channel use. And equation 2.36 is the C complex in the unit bits per second. Okay, are used in subsequent chapters. In the next chapter, we examine these capacity formulas in detail and use them to gain fundamental insights into MIMO communication system performance. Okay, and these are references. Okay, so we have finished teaching chapter 2. Do you have any questions? Okay, if you do not have any questions originally, I should give you homework 2 after chapter 2. But I do not finish preparing the homework 2 yet. Okay, so we will announce the homework 2 in the class this Thursday. Okay, so now let us go to chapter 3. Okay, so everyone, please open the slides of chapter 3. Okay. So in chapter 3, we are going to talk about the applications of the MIMO capacity formula. So please note that the MIMO capacity formula we have derived in chapter 2 is not just a theory. Okay, it has some applications. Okay, introduction. In this chapter, we study the MIMO capacity formula derived in the previous chapter. Okay, that is chapter 2. To see what insight can be gained about MIMO communications. Okay, so what is the meaning of insight? Okay, simply it means that you can see deeper into the MIMO capacity formula. Okay, in order to study the MIMO capacity formula, it is necessary to make assumptions about the type of channel state information CSI that exists. Okay, so first let us go to section 3.1, MIMO capacity under the CSIR assumption. Okay, under the CSIR only assumption. Okay, what is the CSIR? Okay, that is only the receiver knows the channel state information, and the transmitter does not know the channel state information. Okay, You may ask what is the channel state information. That is, it means the channel matrix H. Okay, it is 25 minutes. See you next time. Goodbye.